Hello. Our next talk is by Sahana Balasubramanya. Sorry, it took, I don't know, from University of Münster. And the talk is titled Property NL for Hyperbolic Actions.
So thank you very much. I'm very happy to be able to talk about my work at this conference. And the work that I'll be talking about today is joint work with Francesco Fourier and Anthony Genevois. So in the field of geometric group theory, it's a very common tool that people try to understand a group via its action on some metric space, rather than directly using the algebra of the group in order to understand it. So it's a very natural question to ask ourselves that if we're handed our favorite group G, can we describe all of its actions on some hyperbolic space? And we restrict ourselves to isometric actions on hyperbolic spaces because traditionally the fact that the action is isometric has some very strong implications for the action in question. And in order to avoid repeating saying isometric actions on G on some hyperbolic space, I'm just going to shorten it to hyperbolic action. But it's understood that this is an action by isometries. And in case someone needs a refresher, for hyperbolic actions, the work of Gromov states that this action can be one of 5 types. It can be elliptic, parabolic, lineal, quasi-parabolic, or of general type. And what distinguishes these 5 actions from one another is the presence or absence of loxodromic elements and how those loxodromics behave. So to be a bit more precise, first of all, what's a loxodromic element? Well, a loxodromic element is one essentially that has an infinite quasi-axis in our space. So if we take an element, which is an infinite order element, and we look at its orbit in this group action, then it essentially looks like a bi-infinite line, and it defines these 2 distinct points on the boundary of a hyperbolic space. Essentially, the map into Z from the powers of the element is a quasi-isometric embedding. And in an elliptic action, which is the first one in this list, there are no loxodromic elements, and in fact, the entire orbit of the group is bounded. For parabolic actions, we still don't have loxodromics. However, we are characterized by an unbounded orbit. So that's the blue circle that you see in this picture. This is an unbounded orbit because this picture kind of goes off to infinity, but it doesn't contain a quasi-isometric embedding of C. So it contains no loxodromics. The third action on this list, which is lineal, that's the first action on this list that actually has loxodromic elements. But the characteristic of that action, as the name suggests, is the fact that any loxodromics share the same quasi-axis. So if you have one loxodromic element and you pick another loxodromic element, it acts along the same quasi-axis as the first one that you pick. So in a sense, the orbit of the group looks like a thick quasi-line. And quasi-parabolic, which is the next one, is where you start to see the emergence of independent loxodromics. So loxodromics whose axes are not the same are what we call independent. And in a quasi-parabolic action, which is sort of the red lines in this case, there you have a lot of independent loxodromics, but there's this one point on the boundary that's common to all of them. So the quasi-axes kind of merge in one direction. And the last type of action is a general type action. That's the one that you see in this picture, and that's characterized by the presence of loxodromic elements whose axes are completely disjoint. So in this picture, it would be this one, for example, and this one. Although there's work that shows that if you have 2 strictly independent loxodromic elements, then you have infinitely many. So in order to be able to answer our question, we need to understand, given a group G, how can it possibly act in one of these 5 ways on some hyperbolic space? And even though this question is pretty natural and pretty simple to state, it's extremely non-trivial to answer. And one of the first obstructions you sort of run into is the presence of lots of trivial actions, because you can take any group and take any metric space and have the group act vacuously on the space. It is an isometric action, but it tells you nothing about the geometry of your group, unfortunately. And for countable groups, there's a way that you can construct lots of inequivalent parabolic actions. If someone's interested, you can go take a look at the Groves-Manning combinatorial Horoball construction. But besides these pathologies, it turns out that even groups with well-understood rigid structures can admit lots and lots of hyperbolic actions. In particular, if you're an acylindrically hyperbolic group, I'm not going to define that. That's a generalization of hyperbolic and relatively hyperbolic groups. But if you are an AH group, then there's work which was done by me, Dennis Osen, and Carolyn Abbott that shows that such a group has uncountably many hyperbolic actions that are inequivalent. And even if you drop to a better understood class of groups like solvable groups, there's work done by me, Carolyn Abbott, and Alex Rasmussen that show that these admit lots of focal or quasi-parabolic actions. And in particular, trying to completely classify all of the hyperbolic actions for a general solvable group is sort of one of the long-term goals of the joint work that I'm doing with Carolyn and Alex. So a question that was posed to us by Yash Lodha when I was giving a talk on work that I did with Alex and Carolyn is, besides finite groups, which groups admit very few hyperbolic actions? And morally, this word few could mean one of two things. Few could mean that the group can only act elliptically or parabolically on a hyperbolic space. And these are the two cases that you absolutely cannot rule out, because you can always construct elliptic actions, and you can also always construct parabolic actions either by using combinatorial Horoballs, or there are constructions that give you parabolic actions on trees if you're not finitely generated. So that's one school of thought, the absence of loxodromic elements, that the only actions that G admits don't contain loxodromics. And then there's another school of thought that emerges from joint work that I did with Carolyn and Dennis, which requests that a certain poset, which is denoted H of G, and is called the poset of hyperbolic structures of a group, is trivial. Now, I don't need to actually formally define what this poset is for the purpose of this talk, so I'm going to skip over that technicality. What I will say is that morally, this poset, its elements are equivalence classes of hyperbolic actions, which happen to be co-bounded. So there's that added quantifier co-bounded there. And the equivalence classes are basically ones that respect the coarse geometry of the action. And the partial order on the poset amounts to understanding which action retains more information about the geometry of the group. So in this poset, the trivial action will be the smallest, and actions that retain more information about the algebra and geometry of the group are the ones that will be larger or higher up in this poset. So what we call property NL, which stands for no loxodromics, is precisely condition 1 here, that you don't admit actions with loxodromic elements, and that's where the terminology NL comes from. And the reason we're interested in studying property NL to answer part of this question and not when is H of G trivial is because 1 actually implies 2. And the reason is, if you have property NL, then parabolic actions are unfortunately never co-bounded, so they don't turn up in this poset at all. And so this poset only consists of the equivalence class of the trivial actions, and that's a singular equivalence class. So it is trivial because it's a singleton. So that's the reason we're interested in property NL, because it provides part of the answer to understanding which groups admit few hyperbolic actions. But we're also interested in a slightly stronger property than property NL, which is what we call hereditary NL. And that's the requirement when the group, of course, has NL, but every finite index subgroup has it as well. And why are we interested in this hereditary property? Well, because one of the things we know about the poset H of G is that it's structure is not well preserved under taking finite index subgroups. And as an example, there's this, where the poset on the left-hand side is the poset of hyperbolic structures for the infinite dihedral group, direct sum or direct product itself. And there's only a finitely many set of hyperbolic structures here. But if you drop to an index 4 subgroup in this group, which is isomorphic to Z cross Z, then the cardinality of the poset suddenly jumps to being uncountable, because you can construct many, many linear actions for Z cross Z by projecting the slopes of different lines through the origin in the Euclidean grid. So the structure of this poset, unfortunately, is not preserved well under commensurability. So if we study the property hereditary NL, not only do we know that the poset structure for the group is trivial, but it's also trivial for every finite index subgroup. So that goes towards partially answering an open question of when this poset is preserved under finite index. And that is provided by the class of hereditary NL groups. So you can think of it as a class of groups that have a certain property in terms of their hyperbolic actions, and that's well preserved under commensurability. So I've just given you a definition of a new property. Let's see some examples. And there are some very obvious examples that we have and some that already exist in the literature. And the most obvious example are, of course, finite groups, which are torsion groups. It's pretty easy to check that any amenable perfect group, such as those constructed by Yushchenko and Monod, will also have this property NL. And it follows from the work of Thomas Hadl, Girardel, and Horbez that higher ranked lattices like SL and Z also have this property. And for the same reason in finite groups, if you consider finitely generated torsion groups, like the ones listed on the slide, those are not just NL, but of course also hereditary NL, because they don't contain infinite order elements, so you can never have loxodromics. So what we're trying to do is initiate the formal study of this property in a systematic manner. So what are some things that we can show about property NL and its hereditary version? Well, the first thing, which is one of the things we're interested in, is the stability of this property under some standard group operations. And to this end, we can show that we get a lot of control, that the hereditary version is preserved under many group operations. So is the property NL itself. However, the property NL is not preserved under commensurability, unfortunately, but not unsurprisingly, nor is it preserved under quasi-isometric groups. So you can have quasi-isometric groups where one has the property NL and the other does not have the property. And for amenable groups, it turns out that this property NL has a very nice classification. The group is hereditary NL if and only if it does not virtually surject onto Z. And in particular, if your group is abelian, then the hereditary version of the property is the same as having the property. So for abelian groups, you don't need to check two different things. Having one is the same as having the other. And you might wonder, okay, we've defined this property and we have some examples that exist in the literature, but how big is this class of groups really? So what we're able to show is that every group quasi-isometrically embeds into a group that has the property of being hereditarily NL. So it's actually a pretty large class of groups, and they can contain as subgroups, pick your favorite group. And it turns out that our property also has some relation to fixed point properties. If the group is finitely generated and has property NL, then it also satisfies Serre's property FA, which means that any action of the group on a tree has a global fixed point. But perhaps most importantly, what we're able to do in our work with Anthony and Francesco is that we can greatly expand the list of examples of groups that are hereditarily NL. And the first thing that we're able to show is that Thompson's groups T and V are hereditary NL. We cannot expect Thompson's group F to have this property because Thompson's group F has abelianization Z cross Z. And the fact that Z cross Z has so many linear actions means that you can always portion through the factorization of F and produce lots of lineal actions, at least with loxodromic elements. So there's absolutely no hope for F to be in this list, but Thompson's groups T and V are in this list. And then we're able to show that a whole host of examples that are related to Thompson and Thompson-like groups also have this property. So we have the Higman-Thompson group, the twisted Brin Thompson and Brin Thompson groups, the golden ratio Thompson groups, Stein-Thompson groups. There are a couple of more that we're working on and including in our paper. But what's common to all these examples is that they all exhibit some common behavior that we can study under one broad umbrella. And what that umbrella is that we develop a dynamical criterion for groups that act via homeomorphisms on a compact Hausdorff space. So that includes the Cantor set and the circle, which is exactly what is happening, at least for the groups T and V, and it happens for the other examples mentioned on the last slide as well. And this dynamical criterion, it has a fairly technical description, but the idea is that if you understand that the group acts via homeomorphisms with high transitivity and certain disjointness properties, then that dynamical criterion very strongly controls the algebra of your group. So as an example, you can show that if this dynamic criterion is satisfied, then the group is boundedly generated. And once you can control the algebra of the group, you can actually control the hyperbolic actions. So it's an interesting series of consequences where you start with groups acting via homeomorphisms, which is seemingly so different from our end goal of hyperbolic actions. But then because the algebra gets controlled by the actions via homeomorphisms, so do the hyperbolic actions. And then in order to conclude property NL, or its hereditary version, we need some additional information on the quasimorphisms of the group. So for example, in the case of T and V, what this dynamic criterion buys you is that it completely eliminates general type actions. So those groups cannot act with a general type action. But then the fact that those groups are uniformly perfect and therefore have no unbounded quasimorphisms allows you to eliminate lineal and quasi-parabolic actions as well. So something that's known about the cohomology of those groups is somehow also helping us in the process. And that's basically how we end up proving that this long list of examples that was on the previous slide also have this property NL. So what are some questions that we'd like to understand in this body of work? Well, the first that we'd like to understand is what is the connection between hereditary NL and actions on products of hyperbolic graphs? And the reason this is interesting is because if you have a finite index subgroup of your group G, then it's not always true that you can, starting from an action of your subgroup, construct an action of your parent group on a hyperbolic space. But what you can do is construct the action of the parent group on a direct product of hyperbolic spaces. So if H is finite index in G and H has an action on X, then you basically take the space that looks like X times itself, where the number of repetitions or the number of factors is the index of G and H, of H and G. And then that gives you an action of G by the permutation of the factors. And if the original action of H had a loxodromic, then that element survives as a loxodromic for the action on the product. So there's an obvious connection between these properties, but it's not clear what is the full extent of that connection. And ideally, in an ideal world, we'd like these two things to be equivalent to each other, but it's not clear whether that's true or how we can show that. The second thing that's really interesting, which again exists in the literature to a very large extent, is the connection between being hereditary NL and actions on finite dimension CAD0 cube complexes. So there's lots of interesting results in the literature that start with certain kinds of actions on finite dimensional CAD0 cube complexes, and then they conclude certain fixed point properties of the group in terms of hyperbolic actions. But the actions that are typically considered in the literature are either proper or they need the action to be essential, and there seem to be these added quantifiers that help them get the final result. But the point is that they're almost always ending at some kind of rigidity or fixed point property of the group. And it'll be interesting to understand where this property of being hereditary NL fits in the large picture, because you could think of being hereditary NL as a fixed point property in the following sense, that either the orbit is bounded, which is the elliptic case, or in the case of the parabolic action, there's a unique fixed point on the boundary of your hyperbolic space. So it is a kind of fixed point property. So it would be interesting to understand that connection. Something that isn't mentioned on the slide, but we also talked about yesterday in our meeting with Anthony and Francesco, is that there might also be a connection between being hereditary NL and restrictions that a group could have on being an HHG. The idea being that if you don't admit loxodromics in any hyperbolic action, then it should be impossible to deconstruct your group into hyperbolic spaces, which morally means that your group should not be able to be a HHG or a hierarchically hyperbolic group, if you're familiar with what those are. But another thing that we'd like to understand is how far can we generalize this dynamic criteria that we have? We have it in a very specific setting where you act by homeomorphisms on a compact Hausdorff space. And can we weaken any of those conditions or try to apply a similar criterion but in a different setting for groups that maybe don't act via homeomorphisms? And can we still conclude that the group is hereditary NL? So how transferable is this criteria, and how much can we get away with? So those are some of the questions that we'd certainly like to understand for the future, which is something Anthony, Francesco, and I have certainly talked about. But I'm going to stop here because I'm almost out of time. Thank you.
Okay, let's thank the speaker. So we have plenty of time for questions. Does anyone have any questions for the speaker?
Yeah, hi. So it's a nice talk. So, so can you give some examples of groups which does not have this property NL or hereditary NL, except the obvious one like the hyperbolic NL?
Yeah. So any group that virtually surjects onto Z will fail to have this property. So take your favorite group and take a semi-direct extension with Z with an infinite cyclic group, and that group will fail to have property NL. So many solvable groups will fall into this category. So you could take Lamplighter groups, solvable Bompsog-Solitar groups, generalized Bompsog-Solitar groups. Those will all fail to have this property.
I see. Any group subjects onto that criteria? Okay, that's an if and all. Yes.
Yeah. You could also take free groups. I mean, they will have general type actions, so you'll have many loxodromics. In fact, if you pick any free group, any non-elementary free group that happens to be an acylindrically hyperbolic group, so you can actually construct uncountably many general type actions on a hyperbolic space.
Yeah, right. Yeah, those are. Yeah, thanks.
Sure.
Do we have any other questions for the speaker? Okay, if there aren't any other questions, let's just thank the speaker again.